So here we're going to look at the greatest possible measurement error, so GPE. It's basically if we have a value, what's this kind of maximum error that we could have associated with that value. Now in terms of error and how we describe it, it's this value that we can go above or below a number by. So it's that if we have some measurement, how far above or below can we expect in terms of error? So with that, let's kind of explore some ideas and then we'll get into the math of it. So let's say you took a measurement and the measurement was 36. So you rounded to the ones place there. So you couldn't get anything beyond 36. 36 was the most accurate you could get in terms of taking the measurement. So what are values in the tenths place that would also round to 36? So the idea is that maybe our rounding tool just doesn't have the information or enough information, but we see it's landing at 36. If we had a tool with more accuracy, if we could get accuracy to that tenths place, what's the equivalent of this 36? So where we have this measurement of 36, what we're saying is if we did 36 point something, what values can I plug in there that will also give me 36? So for example, if it was 36.0, something that's exactly correct, that would round to a whole number of 36. 36.1, that also rounds to 36. In fact, I'm going to get rid of that decimal and box there. 36.2 also rounds to 36. So the idea of if I had these values in the tenths place but wanted to round to the ones place, these would work together nicely. 36.3 and 36.4. So all of those would round to 36. Now there are some other options, because if we think in terms of a number line here, let me get kind of a visual for us. If I have 36 right here, up here's 37, and down here's 35. We just grabbed these values over here, and it's basically all of the values up to but not including 36.5, right? At 36.5, then we're rounding to 37. But it's like if we zoom in super close and we got all the way to like 36.499999999, this technically goes to 36, because if I'm rounding to the ones place, I'm only really looking at that 4 as my test digit, which would tell me to round down, and I'm looking at 36. So the idea being here that in terms of collecting values that round to a whole number of 36, we have everything up to 36.5 but not including it, and all the way to 36.0. But what we have over here are other values that round to 36, such as 35.5. If I was rounding that to a whole number there, that 5 would round up and it would be 36. And actually, so would all of the values all the way up to 35.9. So kind of like what I drew over here is I could list more possibilities. 36. We could have 35.5 would round to 36, 35.6, 35.7, 35.8, 35.9. And where I'm listing these whole values, it's kind of connected that then I could write anything beyond them, meaning if I had the number 35.623894, I could just keep making up numbers there and go on forever. Oh, sorry, that should be a 35. 35.6, blah, 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 whatever numbers I want to fill in there. It would round, if I'm rounding to the ones place, to a 36, because all that really mattered is that 6 right there because of my test digit. So starting at 35.5, we have more possibilities that round to this whole number of 36. So what we can see here is that this is coming through as the error that can possibly occur if we have this value of 36. We can actually see these possibilities that round to 36 accurately, just if we had a little bit more precision. So all the way from 35.5 up to 36.5. Now something I'm going to use here is that 35.5 is the equivalent of taking 36 minus 0.5. So if I take 36 minus 0.5, that would get me to 35.5. For 36.5, that's coming from 36 plus 0.5. So this notation here, we're going to combine this because it's using the same numerical values. All that's changing is subtraction versus addition. And what we do is we combine this into a single notation that we can have this measurement of 36, but then in terms of error, we can have plus or minus 0.5. So that's notation that we can use to express this possible error that's occurring with this measurement of 36. To get even more precise with this, when we start going looking for GPE, this greatest possible measurement error, what we would do is we would say the GPE is, and it's this plus or minus 0.5. That's how we would express our error here. This greatest possible error that's occurring with this number where we're seeing 36. But what if we had more accuracy? If we go one decimal place further, what would that error be? So let's kind of go through this one more time just to kind of get the idea behind it, and then I'll just show you the calculation that we can do. So what if our measurement was 36.2? So what if we're now going to the 10th place? Then the idea is, what number can I have next to 2 so that this will round to 2? Similarly, what we're going to see up above, as we saw up above, is that to round we can also go below this number. So we're also going to see 36.1, and then with something next to it. The difference is going to be that next to 1, it has to be values that will round it up to a 2, so that we're matching our measurement of 36.2. If we have 36.2, we need to be rounding down so that we're keeping that 2. So what we could have is 36.20. We could have 36.21. So just all of these values in the hundredths place now that will be rounding down. And 36.24, but keep in mind that we're basically going up to, it's like we're almost at 36.25, just not quite there. Then 36.1, we need to be rounding up here, so like 36.15 would work. 36.16, 36.17, 36.18, all of these will round to 36.2. So getting back to that original number. So what we're seeing here in terms of the range of values, it's like the smallest we could see is that 36.15 all the way up to, and what we're trying to do here is round to 36.2, all the way up to and almost including 36.25, just not quite. But in terms of describing our error, we're just going with using the 36.25 for simplicity. So what we have here is this idea of 36.2 minus 0.05 versus 36.2 plus 0.05. So in kind of a shortened notation, we would describe this as 36.2 plus or minus 0.05. So if I wanted to know the GPE, this greatest possible error is, and that's just this plus or minus portion, it would be plus or minus 0.05. So the shortcut for this is that what we can see is here we started with accuracy to the ones place, here we had accuracy to the tenths place, and with that, our error got smaller. Like with rounding to a whole number or having a value that's rounded to a whole number, there's a larger amount of error possible. But the more accurate our measurement gets, the smaller the error is going to get. So there's this relationship here, and it has to do with how far we have accuracy. The more and more accuracy we have with our original number, the less error we can expect. So that's what this is describing here, is that GPE is going to decrease when we increase the level of precision. Okay, so what I'm going to show you is that really we can just use this little trick each time instead of having to list out all of the possibilities and think about what that means. The GPE is always 1/2 the precision. So I'm going to use that for these down here. So we want to find the GPE, so we want to find this plus or minus value. So what we want to do is take 1/2 the precision. So the precision, I'm looking at my significant figures, and really I'm looking at the rightmost significant figure, and I want that place value. So in terms of precision, we have precision to the 100ths place. Now, taking 1/2 of this precision, and just make note, we're not taking half of this number here, it's half of the precision. And if I'm writing out 100ths here, in terms of numerically, that's a 0.01. There is 1/100th. So that's the precision that I'm taking, and then I'm going to divide that by 2. So if I divide that by 2, that's going to be a 0.005, and that's my GPE. So GPE would be plus or minus 0.005. So without having to list out all of the possibilities, that's what we have there. What it would come down to, just to kind of relate it to what we did up above, it'd be like listing out values from, let's see, 4.255, that would round to 4.26, all the way to 4.265, where that starts to round up to 4.27, but it's like we're almost there. If we were just a little to the left of it, then that would round to 4.26 as well. So you can see is that this is coming from that 4.26 in the middle here. If we take away 0.005, that would work. And if we have 4.26 plus 0.005, that would work for that side as well. So we end up with that value. All right, with this one right here, so in terms of precision, let's see, this will be tenths, hundredths, thousandths, 10,000ths. So I'm going to take the precision, which would be working with just zeros and ones, so I'm going to go 0.0001, basically replacing that 6 with a 1 there, and then everything else is 0, and I want to cut that in half. So divided by 2, which will be 0.00005. So that'll be our GPE is plus or minus 0.4 zeros with a 5. All right, this one right here, we have accuracy to the 100ths place. So with that, I'm going to take 1/100th, which is a 0.01, divide it by 2, which is 0.005. So GPE is plus or minus 0.005. And then from there, this number here, where precision is at 100ths again. And you know what? The precision stays the same. If I figure out for the GPE for having something with precision to the 100ths place, it's gonna stay the same. So you can do the math again, but it's gonna stay constant.